And welcome to this GCSE Science revision video for additional chemistry on bonding. In this video we'll cover ionic bonding, covalent bonding, metallic bonding and polymers and nanoscience. So, ionic bonding is when metals react with non-metals. Electrons transferred from metal atoms to non-metal atoms forming ions. These result in compounds called ionic compounds. So some examples is maybe sodium plus chloride, where the sodium gets positive charge, the chlorine gets a negative charge. Or magnesium oxide, where the magnesium gets a positive charge and the oxygen gets a negative charge. Remember, in ionic bonding, opposites always attract. In each of these reactions, the metals atoms give electrons to the non-metal atoms. The metal atoms become positively charged, the non-metal atoms become negatively charged. There is a strong electrostatic force of attraction between these oppositely charged ions called an ionic bond. Sodium ions have the formula Na+, while chloride ions have the formula Cl-. You need to be able to show that the sodium ion and one chlorine ion bond together. In the exam, make sure that if you're asked to draw this as a dot and cross diagram, you remember to draw the electrons from one atom as dots and from the other atom as crosses to show clearly where the electrons have come from. In this example, magnesium ions have the formula Mg2+, while the oxide ions have the formula O2-. You only need one oxide ion to go with one magnesium ion, as the 2- cancels out the 2+ to give an overall charge of 0. In this final example, we have one ion of calcium with a charge of 2+. So therefore, if we are bonding it to chloride ions, you need two of them to cancel out the 2+, as you would need 2- overall. Ionic bonds are the electrostatic forces between oppositely charged ions. For an ionic substance to conduct electricity, the ions must be free to move so that they can carry the charge from place to place. So therefore, the ions either need to be in a molten state, or the ionic compound needs to be dissolved in something like water to make it aqueous, so the ions are free to move. Each ion is surrounded by oppositely charged ions held in place by electrostatic attraction to form a giant ionic lattice. The number of ions in an ionic compound is such that the charge of a sample of the compound is 0. The ions in the crystal lattice are very strongly bonded together, so require a high temperature to be separated, so have a high melting point. If an ionic compound is melted or dissolved in water, then the ions are free, and we can say that they can be electrolyzed. A covalent bond is formed between metal atoms which combine together by sharing electrons. Covalent compounds have no free electrons and no ions, so they do not conduct electricity. Non-metals combine together by sharing electrons. The shared pair of electrons holds the two atoms together. This is called a covalent bond. A group of atoms bonded together is called a molecule. Some examples of covalent bonds which make up in the exam is hydrogen, which is H2, water, H2O, ammonia, NH3, and methane, CH4. 4. A single covalent bond, when drawing it as a structure, is just shown by a single line. Dot and cross models show how a pair of electrons form a covalent bond. In hydrogen, each hydrogen has one electron on its outer shell. Remember that atoms want 4 outer shells. The first shell can hold 2 electrons, further shells out can hold 8. So for each hydrogen, they need to borrow 1 electron from the opposite hydrogen to get their 2 electrons. So in this example, they both now have 2 electrons each. In forming water, or OH2, we go and the oxygen requires 2 electrons, so it must bond with 2 hydrogen ions. This enables it to get 1 electron each, so the oxygen in total gains 2 more electrons, while each of the hydrogen borrows 1 electron from the oxygen to make 2 electrons in their outer shell. In methane, or CH4, the carbon needs 4 more electrons in its outer shell. Each of the hydrogens, as before, needs 1 more, so therefore the carbon will bond to 4 individual hydrogen atoms to gain 4 more electrons. Covalent molecules sometimes form simple molecules. These contain only a few atoms held together by strong covalent bonds. An example is carbon dioxide, the molecules of which contain 1 atom of carbon bonded to 2 atoms of oxygen. The properties of simple molecules are that they have low melting and boiling points. This is because the weak intermolecular forces between them break easily, and they are non-conductive. So substances with simple molecular structure do not conduct electricity. This is because they do not have free electrons or any overall charge. Hydrogen, ammonia, methane and water are also simple molecules with covalent bonds. They all have very strong bonds between the atoms with much weaker forces holding the molecules together. When one of these substances melts or boils, it is these free or weak intermolecular forces that break, not the strong covalent bonds between the atoms. Simple molecular substances are gases, liquids or solids with low melting and boiling points. In giant covalent structures, they contain a lot of non-metal atoms, each joined to the adjacent by covalent bonds. The atoms are usually arranged into a giant or regular lattice, which is extremely strong because of the many bonds between each individual. Properties of giant covalent structures are that they have very high melting points and that some of them can conduct electricity if they have free moving electrons, such as graphite. Graphite is a form of carbon atoms that forms in layers. These layers can slide over each other, so graphite is much softer than diamond. It is used in pencils and in lubricants. Each carbon atom layer is joined to only 3 other carbon atoms, so therefore in between the layers there are free moving electrons, so graphite can conduct electricity. Diamond is a form of carbon in which each carbon atom is joined to 4 other carbon atoms, forming a giant covalent structure. As a result, diamond is very hard and has a high melting point. It does not conduct electricity. Silica is found in sand and has a very similar structure to diamond. It is also hard and has a high melting point, but contains silicon and oxygen atoms instead of just carbon atoms. The fact that it is a semiconductor makes it useful in the electronics industry, as most transistors are made of silica. Buckminster fullerene is yet another allotrope, or different arrangement of carbon atoms. It is actually not a giant covalent structure, but a giant molecule in which carbon atoms form pentagons and hexagons. This makes it into a ball which is hollow inside. Because it's a ball, it's very useful in lubricants and has many other properties. Metals form giant structures in which the electrons in the outer shell of the metal atom are free to move. The metallic bond is the force of attraction between these free electrons and the metal ions. Metallic bonds are strong, so metals can maintain a regular structure and usually have high melting points. The diagram shows how the negative electrons have disassociated from the outer shell of the metal ions, causing the metal ions to be positively charged. This sea of delocalized electrons is able to move through it, so can conduct electricity and heat through metals. Metals are good conductors of electricity and heat, as previously stated, because of the free moving electrons. The free electrons allow metal ions to slide over each other, so metals are malleable or ductile. Nanoparticles range in size from about 100 nanometers down to 1 nanometers. They are typically the size of a small molecule and far too small to see with a microscope. Nanoparticles have many uses. Nanoparticles have a large surface area compared with their volume, so they are often able to react very quickly. This makes them a useful catalyst to speed up reactions. For example, titanium oxide nanoparticles can be used to coat windows and cause dirt on the windows to break down. Nanoparticles also have different properties to the same substance of a normal sized piece. For example, titanium dioxide is a white solid used in house paint and certain sweet coated chocolates. Titanium nanoparticles are so small that they do not reflect visible light, so cannot be seen. They are also used in sunblock creams or to block harmful ultraviolet light without appearing white on the skin. Nanoscience may lead to the development of new catalysts, new coatings, new computers, stronger and lighter building materials, and a wide range of other things. A lot of everyday items are made of polymers. Many of these polymers are not biodegradable by microbes, which means that microbes will not break them down or decompose them. Polymers are usually disposed by burying them in landfill sites or burning them in incinerators. These methods of disposal cause environmental problems and waste valuable resources. Monomers can join together to form polymers. So, for example, addition polymers are formed from alkenes. This is where something like ethene is polymerized together to form polyethene. There are two main types of polymers. Either high-density polymers, where many polymer strands are interwoven together, or low-density polymers, where less are woven together. High-density polymers are stronger. Low-density polymers are weaker and more flexible. So remember, when revising, start early, turn off distractions, keep questioning yourself using question cards and flashcards, and quality of revision is better than quantity of revision. Good luck with your chemistry exam.